So Dieter Rautenbach is with us today to talk about maximum matchings, one of the fields that he is an expert in, one of the many fields. His chapter in our edited book on topics in algorithmic graph theory also has to do with matchings. And I encourage all of you to go ahead and read his chapter after being inspired by today's talk. So Dieter, the floor is yours.
Okay, thank you. The chapter in the book is about restricted types of matchings. So matchings that additionally satisfy some structural properties. If you look at the subgraph induced by the vertices covered by that matching. But today is really a talk of a very classical flavor. So this is just about ordinary matchings and a very nice classical result in that area, namely the Erdős-Galay bound. So let's first start with let's first start by mentioning the co-authors. One of the co-authors actually is in the list of the people listening to the talk today. It's Johannes Pardai, who is sitting in another office here 5 meters away from me. And the results I'm presenting are joint work also with Stéphane Bessy from Montpellier and Luca Piscararieta, who was at Montpellier at that time, but he moved now to Sofia Antipolis. And we did this this summer. Okay, so the title is Factorially Many Maximum Matchings Close to the Erdős-Galay bound. So this means that we want to count matchings. And here are some results concerning the number of maximum or the number of perfect matchings in graphs, which is actually a very nice area, which has some very strong and beautiful conjectures and results in it. So one thing that has to be mentioned clearly is that counting perfect matchings, even in bipartite graphs, is a very difficult problem. So this is a classical result from the area of counting complexity due to Valiant from 79, that counting the number of perfect matchings in a bipartite graph is number P complete. There are some beautiful conjectures which actually also come from other areas, like there was van der Waarden's conjecture on the permanent of doubly stochastic matrices, so matrices where the sums over the rows and the columns always give 1. And if you look at this formula here, so this looks like the determinant of a matrix without the sign. So if you would add the sign here, then you would get the ordinary determinant. And if you remove the sign, then this expression essentially counts the number of perfect matchings in a bipartite graph where you use the adjacency, the bipartite adjacency matrix. And van der Waarden had a conjecture concerning a lower bound on the permanent of a doubly stochastic matrix. And this was proved by these two people in the beginning of the 80s. And if you apply this to bipartite graphs, then you take the bipartite adjacency matrix of a D-regular graph, then you can scale the rows and columns so that you get a doubly stochastic matrix. And then you get, as a consequence of this proven conjecture, that D-regular bipartite graphs have exponentially many perfect matchings, if D is at least 3. There is also an upper bound on the value of a permanent that was shown by Bregman. And this gives you also an exponential upper bound on the number of perfect matchings in D-regular bipartite graphs. And not so long ago, just a decade ago, Luis Perret, František Kardoš, King, Dan Kral, and Sergei Norin, they proved the conjecture of Lovász and Plummer, namely that in a cubic bridgeless graph, you have exponentially many perfect matchings. And just remember that this is one of the earliest results in graph theory. Peterson proved in 1891 that there is one perfect matching in cubic bridgeless graphs. And these people, they have shown this conjecture by Lovász and Plummer. And it's actually very beautiful and very complicated to achieve this result. So you see that counting perfect matchings or counting maximum matchings is a classical area with beautiful results and deep theorems. And here is now this result of Erdős and Gallai, which comes from a very early paper that I've been looking at several times, because this paper contains several beautiful results. Among others, the following statement. If you take a graph with n vertices, m edges, and matching number nu of g, and you write the matching number as in terms of the order, so you write the matching number in this way here. So you take the number of vertices, and then you look at the factor that you have to put here to get the matching number. Then this factor nu will clearly be some value from 0 and 1/2, because the largest matching being perfect has exactly n/2 many edges. Okay, then Erdős and Gallai have shown that the number of edges of your graph cannot be too large. It is upper bounded by a function which depends on these two parameters, the number of vertices and this parameter measuring the size of the matching in terms of the order. And here is the upper bound. And if you look at this upper bound, then there are two things I want to point to. First of all, you have two different ranges. You have a first range which covers all the cases of a relatively small matching number, which goes up to something like 0.4n. So if the matching number of your graph is roughly below 0.4n, so it's a little bit below perfect, then you get this expression. And if you look at this expression, then you immediately see that this is the number of edges in a complete bipartite graph. And this is the number of edges in a clique. This also tells you more or less how the extremal graph will look like. And then if the matching number is getting closer to being perfect, to having a perfect matching, then the behavior is different. Then you have just a big clique, which will be extremal. So here are illustrations of the extremal graphs, which are actually unique. One is constructed by taking a clique of size matching number and connecting it completely to an independent set containing all the remaining vertices. So this part here is a clique, and between these two sets you have all the possible edges. And this is for this first range. And in the second range, you just take a big clique and the number of vertices is such that you have not quite a perfect matching in it, but an almost perfect matching. And these are the two extremal graphs for that theorem. Okay, so if you look at this result, if you look at these extremal graphs, and of course the matching number is exactly this value nu of g, but you can actually easily calculate the number of maximum matchings that you have in this graph. So if you look at this graph here, then every maximum matching connects the vertices in this part to vertices from this part. And you can build up a maximum matching actually one by one. You start with the first vertex and you have this many choices for the matching partner. Then having chosen one element in here and fixing this edge to be part of the matching, you can look at the second vertex. Now you have one less choice for the matching partner. So you see that you get a factorial behavior. Okay, so you have this many maximum matchings actually in this graph. So the first guy has this many choices, and then the number goes down 1 unit with every further vertex. And also for this graph here, this is a simple exercise. How many maximum matchings do you have in a, or how many, in a complete graph of odd order? And there's actually a very nice or simple way of convincing yourself how many matchings you have. So take a look at these vertices here. All the other vertices are isolated, and just look at any permutation from 2 times matching number g plus 1. So you look at any permutation of these vertices. You have an odd order, so you remove one vertex and you ask how many perfect matchings do you have in the rest, and you can do this for every vertex of that graph. So here we can assume that we have an even number of vertices remaining. And then if you look at any permutation, then you can take the pairs of consecutive vertices to form the edges of your matching. And then, of course, which of the two places a vertex has landed on doesn't matter. So you can swap these vertices in each of these positions. And you can also exchange these pairs completely and repermute them. So if you think about this argument, then you see that the number of maximum matchings in this graph here has this form. So this corresponds to the number of permutations. And then here you cancel out those permutations that lead to the same matching. Okay. So if you look at these two things, then of course the expressions are different. But if you manipulate these expressions a little bit, then it is not difficult to see that the number of maximum matchings is between these two expressions, which are factorial in terms of n and the matching size. So this upper bound looks very much like this. And here also you have a similar lower bound. And the only difference is that here you have some factors which, of course, have a large impact in expressions of this form. So you see that if you are in this extremal situation, then you have factorially many maximum matchings. Okay, and this observation was the starting point for the results we came up with. And the idea was that if you are close, if you fix the order, the matching number of the graph, and you now require that the number of edges in your graph is close to the upper bound given by the Erdős-Galai theorem, then the idea was that somehow this should force the graph to have a structure which is comparable to one of these two pictures here. And then we hope to show in that situation as well that there are factorially many maximum matchings. And this is what we did. So here's the general idea. If this difference is small, so if your graph has close to this upper bound many edges, then the question was, do we still have factorially many maximum matchings in the graph? And here are two results. So the first result works in the complete range of the possible values for this parameter nu. Remember that this is between 0 and 1/2. 1/2 means that the graph has a perfect matching. And now we have this statement. So here we say, this number here you should consider fixed. So this is a fixed value. Now this here means that the graph should have sufficiently many vertices in terms of this fixed value nu. And here we say that the number of edges of your graph is sufficiently big. So it can be smaller than this value, but only by a small quantity. So only by this small quantity here. And if this is the case, then really the graph has factorially many maximum matchings. And this was somehow the first result we obtained. And if you look at this, you can ask yourself, especially looking at these constants that appear in the result, and looking at this bound here, does this make sense? Is this the right function to subtract? Are the quantities measured in the right way? And one observation is that this function here, the number of that appears in the Erdős-Galai bound, this has this form here. So it's a constant times nu times n square. So one thing that one might not like about this expression we are subtracting is that nu enters this expression squared. But keep in mind that nu is just a small constant. So this only has a big impact if you talk about really small values, which are close to 0. Okay, so that's one thing. What's the next observation? Yeah, so as I've said, so actually this is the same thing. At the moment, this results looks at this kind of thing, but we would rather have something which is of this form. And then if you look at this statement, then it might look strange that it has some hardwired constants in it. So the value 50 that appears here and the value 0.1 that appears here. It is not difficult to take the very same proof and replace the number 50 by some constant capital M, and to replace this value 0.1 by something which will eventually depend on this value capital M. But we didn't do so because even if we increase this value M to be very large, the improvements that we see here are not, we don't get close to the to the right bound. So in order to prove the best possible version of this result, one surely will need further ideas and exploit further methods. Therefore, we kept this result in this form. But here is a second result, which already takes care of some of the drawbacks of this result here. And it has a different form. So there are two functions, h of nu and h nu and h delta. The first one takes in one input, and the second one takes in two inputs. And the statement is the following. So if you fix epsilon to be your favorite small number, then the first function here will tell you an upper bound on this interval. And if you pick this parameter nu, measuring the size of the matching from this range, so this is intuitively, this means if epsilon is small, then the interval will get shorter and you will be allowed to pick only smaller values of nu. And now you can take these two values and plug them into this function, and you get the following statement. If you have a graph of order n, size m, and matching number nu times n, such that first of all, it has sufficiently many vertices, and secondly, the number of edges is not too small, so it is the Erdős-Gallai bound minus a small fraction of n squared. And here in this small fraction, the value that you have to require, it depends on these two values that you pick first. You first pick the epsilon, then you get the range for the nu, then you pick the nu, and then you get the value that you can put there. But the result then is quite strong. The number of maximum matchings that you get in this situation is essentially close to the upper bound that we had. Remember that the upper bound was something like this. So falling factorial n to the nu times n. And here you can get a factor which is as close to 1 as you like. But of course, this result tells you that you get close to the upper bound if you push down or push some values to extremes. But that's maybe the kind of result that you would like to have in that range. Okay. So let me, so both results, they establish what we want. If the number of edges is close to the Erdős-Gallai bound, then you have factorially many maximum matchings in the graph. And let me explain a little bit about the proof. So it is based on a very beautiful result in matching theory, namely the Gallai-Edmonds decomposition. So it is based on three sets. The first set D contains those vertices that are missed by some maximum matching. So if you remove the vertex from the graph, the matching number doesn't change. This means that there is a maximum matching avoiding that specific vertex. That's the set D. Now you have look at the neighbors of D. This is the set A, and you look at all the remaining vertices. This is called C. And if you have this partition, then what you should do is look at the components of the subgraph induced by the set D, and let's call them G1 up to Gk. So we have K components in the subgraph induced by D. And then the statement is that every maximum matching of the graph has a very beautiful structure. It consists of almost perfect matchings of the components G1 up to Gk, because each of these components is in fact a factor critical graph. So it has odd order, and no matter which vertex you remove, you still have a perfect matching to cover the rest. And every maximum matching of the graph G contains an almost perfect matching in each of these components, leaving exactly one vertex uncovered. And then you have additionally matching edges that connect all the vertices from A to the uncovered vertices in D. So if let's say you have 3 vertices in A, then each of them gets connected to a different component G1 up to Gk. And some of these components will contain uncovered vertices, which is because your graph doesn't have a perfect matching. And the third part is that you have a perfect matching inside the part C. So every maximum matching of the graph has a perfect matching covering all of C. without any connection to A. So you don't see any of these edges. You don't see edges of this type. And up here you have these almost perfect matchings, and you connect some of the remaining vertices down to A, and this will cover all of A. Okay, so that's the Galley-Edmonds decomposition. And now you can ask yourself, how many vertices does a maximum matching leave uncovered? And let's go back to this picture. So every maximum matching covers all of C, and it covers all of A, and it covers for each component, G1 up to GK, all vertices but except one. And then some of these vertices will get matched to A. So the number of unmatched vertices is exactly the number of components that you see in that part minus the number of elements that you see in A. So this difference here is the number of uncovered vertices. Another way of writing this is n minus 2 times nu. So this is exactly k minus A. Now take this decomposition and construct a graph by adding as many edges as possible without changing the structure of the decomposition. So we construct this graph G star by taking each of these factor critical components and making it a complete graph. So the order was odd, and we now plug in all the remaining edges to make it a complete graph. Furthermore, the edges between A and D, they form a bipartite graph, and now we add all the possible edges between these two sets. And finally, we make this part here also complete. So what we are doing here is we add all the edges to that decomposition that do not change the matching number, and they do not change the decomposition. If you take this graph G star and you look at the Galley-Edmonds decomposition of it, it's exactly the same decomposition as for the graph G. And now count the number of edges of G star. This is now very easy because all these components G1 up to GK, they are complete. So you have this many edges in each of these components. Then you have all possible edges between A and D. And you made A union C complete, which means that you have exactly this many edges there. Okay. And now look at this expression here. So you have these components G1 up to GK. They are small complete graphs. And how large can this value be? The largest is when you move all the vertices, let's say, to one component. You make one of these components as big as possible. And all the other components, you just keep one vertex. So the component doesn't disappear. The number of components stays the same, it's k. But you remove all the vertices to one big one, making the number of edges in that part larger and larger. And if you do so, then you have exactly this many edges. So this will now be the number of edges in the big component that you have in that part B, and all the remaining vertices are just isolates. And of course, you have this inequality here. Okay, this value that you see, we call M star. Now, clearly, by the result of Erdős and Galley that I started with, this number M star is still lower equal the maximum number of edges that you can have in a graph with these parameters. Because this number of edges here, it corresponds to a graph which has the same matching number, exactly the same matching number as the graph that you started with. So this inequality here follows from the Erdős-Galley result. This inequality here follows from the fact that shifting these vertices increases the number of edges. And G star arises from G by adding edges. Okay, so what does this tell you? This tells you that if the number of edges in your graph is not much smaller than this value here, so in other words, this difference is upper bounded by a small quantity, then you can write this difference as the sum of three terms. First of all, this value minus M star, then M star minus MG star, and then MG star minus M. And this inequality here, first of all these three terms, they are non-negative, and their sum is small. So this will tell you that each of these three terms must be small. So this term being small, the first term on the right hand side being small, so it doesn't It doesn't update now. Let's see. So there is a, okay, now it's working. Now it's back. Okay. This term here being small means that when you go from the graph to the graph G star, you didn't add too many edges. So the graph G already looked very much like the graph G star. This term being small means that in this inequality, there's not much space. In other words, when you started with these components G1 up to Gk, and you moved all the vertices to form one big component and leave isolated vertices in the other ones, you didn't do too many changes. You didn't add so many edges. So this quantity being small means that inside of D, you already have a situation where one component is pretty big and the other ones are very small, and one is really dominant. And the last term being small, this means that you have a small difference between these two values, and this also tells us something about the graph, but that's actually the most difficult thing to capture. What does this quantity being small imply? And that's now what we look at in the next statement. Okay, to formulate the next statement, I will introduce some useful variables. So let's look at them. So remember that the matching number is nu times n. So this is the matching number. Minus a. So what is this? So remember that your graph has this decomposition. So here's D, here's A, and here's C. And this quantity here, of course, it is greater equal 0 because the matching number is at least A, the number of vertices in A, of course. No? But it's at most nu. And let's think about, nu times n, actually. And let's think about these extreme situations. What does it mean that you're close to 0? If you're close to 0, then this value is essentially the matching number. So the part of the matching linking A towards D is essentially all your matching, which means that C must be small because C contributes a certain number of edges. You have a perfect matching inside C. So if you're close to 0, then C will be small, and your matching essentially consists of these edges, which also tells you that inside D, you are not adding too many further edges. Okay, and what does it mean that you're close to this value? That the difference is close to nu times n? Then, in fact, you immediately see that A will be small. It is pushed towards 0. And in the extreme case, the set A will be empty, and you will completely decompose the top part from the bottom part. So C will be an induced part that is completely not disconnected from these components there. So the interpretation of this value is that if it's close to 0, then your matching is essentially the matching between the bipartite part A and D. And if the value is close to nu, then the set A disappears and you remain with some essentially complete parts of your graph. And here's another useful variable. So this is the number of vertices in D, and this is the number of components in D. So if you look at this difference, then this tells you the following thing. To create k components, which have odd order, you need at least one vertex for each of these components. So you need k vertices. And then D minus k tells you how many additional vertices are you allowed to place into these components. So in fact, if you have just one big component and all the other components are isolates, then you have exactly D minus k vertices plus one many vertex in that big component. So this somehow tells you, this value y tells you a lot of information about the structure of the part D. Okay. So now, remember that we wanted to look at this difference here because we want to understand what it means that this difference is small. And the first thing we do is that we prove this lemma, namely, we write this expression, this difference, as a function of n squared, where this factor here depends on these two useful variables, and these useful variables, they are derived from the parameters of your graph. And then you still have some linear terms which we're essentially going to neglect. later. So the message of this lemma is that this difference here is essentially lower bounded by something which is n squared times a nice constant. And this constant depends on parameters that describe your graph. And here is the function. Again, you see that you have these two ranges corresponding to the Erdős-Galai bound. And essentially, if you remember the previous page, then we know that epsilon n square will be an upper bound on this quantity. And then with this inequality here, you will see that this factor here will be forced to be small. So you can divide by n squared later, and then you see that epsilon, the value that you start with, will be upper bounding this value here. Okay, so now let's look at this function here, gxy, and let's understand what it means that this function is small. Okay, here's a plot of this function, which is very nice. And here you see the plot for the value nu equal to 0.4. And this is exactly where the two ranges from the Erdős-Galai bound meet. So you had the first range from 0 up to 0.4, and then the second range from 0.4 up to 0.5. And if you're exactly where the two ranges meet, then you have this nice tent that touches the ground in 3 positions. So if gxy is small, then you must be either close to this point or close to this point or close to this point. Okay, so that's the message. Now, what changes if you take different values here? So here you see a plot where the matching number is small. Your matching just has 0.1 times n many edges. Then you see that the tent doesn't touch the ground in 3 positions. So these 2 points, they have moved up. You only touch the ground still at this point. And if you increase the value of nu, then these 2 pins of your tent touch the ground at 0.4. But if you go beyond 0.4, closer to 0.5, then a nice thing happens, then the other point lifts up. So you have this nice function that has this beautiful behavior. If you start with small values of nu, it looks like this. Then the tent touches the ground at 3 positions, and then the last point goes up again. Okay, so for instance, if you are in this situation and the value gxy is small, then you know that this point will not be possible because it is lifted up to away from 0, and you should be in one of those 2 positions here. And that's actually what you can actually quantify. So if your function, so we quantify it in a different way. We say, when is this function big? So when we are far away from 0. If we are far away from 0, so either we are far away from 0, or so either you have this behavior here, unless, and now we describe the positions where we are close to 0. So one option is that we are in the first range with the small values, and the value of x is small, which means that if you remember the plot, then so how was it? So maybe I should not try to do this here, but you had this point of the tent which was in the back, and that's the point where you are now. So this is where you touch the ground, and this is for small values of your matching number. Or if you want one of the 2 points in the front to touch the ground, then you must be in the second range. And then either you are very close to the left, very close to the left, or you're very close to the right. So in fact, these 3 positions here, they describe the 3 points in that picture that I've seen before, where the function can touch the ground. And then you have to keep in mind also the range, the part of the range that you're in. If all 3 points touch the ground simultaneously, then you can be in either of these positions. If the matching number is smaller, then these 2 points were lifted up, and this is the only option to touch the ground. If the matching number gets close to n½ then the other 2 points are relevant. Okay. Now, if you look at these 3 situations, so first of all, here x is very small. What does it mean that x is very small? So remember that x was nu minus a divided by n. So this being small means that your matching is essentially the matching between this bipartite, in this bipartite graph between A and D. Okay, so in this situation, your graph is pushed towards the complete bipartite graph, which has the partite sets of the right cardinality. What happens if this value is very big? If it is close to nu, then remember that the set A was shrinking, and if actually x is equal to nu, then the set A completely disappeared, and your graph is just a union of cliques in some sense. And this here, y being small, means that if you look at the components in D, then they are very small, because y measures how many additional vertices you have in these components on top of the isolated vertices. And if this is small, then D essentially consists of isolated vertices. A has almost disappeared, and what you have is essentially C. So in that situation, your graph is essentially C being everything. And in the last situation, so A is almost disappeared, and y is very big. So what does this mean? Now you take all the vertices from C and move them up to that big component in D. So in that situation, the vertex set of the biggest component in D, which was called G1, this is pushed towards being everything. So you see that now we have a clear understanding of the three terms that are small. So the first term being small means when we go from G to G star, we don't change much. The graph already looked like this, essentially. The second term being small means that inside D, you have one big component containing almost everything, and the other components are very small. And the last term being small means that either A is shrunken away, and you're in one of these two situations where your graph is essentially a big clique. Either it is C or it is this clique here, or A is essentially as big as the matching number, and then your graph is pushed towards this graph here. So you see that now, having decomposed this difference between the number of edges and the Adder-Scalar bound into these three terms, we have a nice interpretation for each term being small, and now we can extract the corresponding information from these terms. So what do we need to do this? So if you look at this part here, this is more or less like a hand-waving bit, because when I say that the graph G is pushed towards this graph, I still don't know how exactly to find factorially many maximum matchings. So I still need a nice ingredient to do this. And here are the nice ingredients that take care of this. So what is the task of these two lemmas? So the first lemma here takes care of the situation when A is essentially close to the matching number. So C is very small. So let's draw it like this. And here we have essentially very small components only, because also D is pushed to be almost equal to K. And therefore, if we just keep one vertex per each of these components, we essentially have a bipartite graph, which is almost complete, because when we constructed this extreme configuration, we didn't add much edges. And then one part of this bipartition has A vertices, and the other part of this bipartition has K vertices. And in between, we are almost complete bipartite. So this corresponds to the first case of the previous lemma. And now let's look at the statement. So you take the complete bipartite graph with A vertices in one side and K vertices in the other side, and you remove a certain fraction of the edges. So the complete bipartite graph has A times K many edges, and you remove a gamma fraction of this. Then you can still prove that you have to do it in a clever way. You don't want to change the matching number. So you remove the gamma times AK edges without changing the matching number. So the graph still has a matching saturating all of A, which means that the matching number is still exactly A. And in this situation, we show with this lemma that there are factorially many maximum matchings, or in this situation, matching saturating all of A. So this takes care of the first situation from the previous lemma. And now we have these other two extremal configurations where the graph is essentially C or where the graph is essentially G1. And both these parts are essentially complete. And then the second lemma comes into the game. So here we look at a complete graph of even order, which starts with a perfect matching, of course. And now we remove a certain number of edges, and the number of edges we remove is this quantity here. So the complete graph has 2p choose too many edges. So you see that allowing this many edges to be removed means that we remove less than, let's say, a %. So a small fraction of edges is removed. And then still this graph, we do it in such a way that we still keep one perfect matching at least. So we don't create any isolated vertices in particular. And then still we have exponentially many maximum matchings or perfect matchings in that situation. Okay, so if you look at this result here, then you see some hardwired constants. And clearly, if you replace this 0.01 by some small value, some epsilon, you can turn this expression here also into, make it dependent on that epsilon. The key in this lemma is just to show the effect and not to quantify it as best as possible. And I would like to explain the proof of the second lemma because it is actually quite nice. And it can be explained with this picture here. It goes like this. So we start with the graph G. So the graph G here, it arises from the complete graph of order 2p by removing few edges. So how many edges do we remove? We remove at most this many edges here. Okay. And we do it in such a way that the graph still has a perfect matching. So let's say that these edges here, the horizontal edges, they are the edges of our perfect matching. And now from G, we construct the auxiliary graph H in the following way. We contract all the edges of our perfect matching. And in fact, we have also selected a left endpoint and a right endpoint for each of these edges of the perfect matching. And when we see both diagonal edges, then we connect the corresponding vertices in H. So every vertex here in H corresponds to one of those edges in our perfect matching of G. And whenever we see this edge here in our auxiliary graph, the corresponding matching edges, they are joined by these two diagonals. So that's the construction of H. Now, how many edges does the graph H have at least? So from the graph K2P, we just remove at most this many edges. And every edge we remove to construct our graph G can only affect one pair of vertices of H. Because if you look at the vertices of H, they correspond to the matching edges. And then if an edge doesn't lie between the two matching edges, then it wouldn't affect the construction of H. So if you think about H, you see that it is constructed in the following way. It starts with P many vertices because we had 2B vertices and we contract the perfect matching. So you start having all edges, and then for every missing edge of G, you subtract at most one edge from the graph H. So you see that you still have, let's say, 99% of all the edges. So it's a pretty dense graph still. And now we can do the following thing. We look at, we use the fact that the graph H is very big to show that it has many matchings. We don't care about the size of these matchings, just many matchings. Because whenever we look at a matching of the graph H, let's say that this is a matching of the graph H, we can associate to this matching a matching of the original graph in the following way. Whenever we have an isolated vertex, then we just copy the corresponding edge of our original matching to be also in the new matching that we construct. And whenever two vertices of H are connected by an edge in this matching here, we use this edge here to perform a swap operation. So originally we had these two edges, and we replaced them by the two diagonals that we actually considered when we constructed the auxiliary graph. Now the proof works as follows. So we start with this graph, we construct this graph here, we observe that it is almost complete, we show that it has many, many matchings, regardless of the size, even small matchings are nice. And for each of them, we get a different perfect matching of the original graph. So if you go through these steps, then you get a large number of perfect matchings of the original graph. And that's the idea of that proof. And in the other lemma that concerned that complete bipartite situation, you just apply a similar argument. So this essentially completes the full range of the argument. So you start with your graph, you look at the decomposition, the Gallai-Edmonds decomposition. You do this perfectly. You change this by forming G star, adding edges without changing the partition. You change V star by pushing everything into one big component. And then you argue that being close to the Erdős-Gallai bound tells you that the graph somehow degenerates to some extent to being either complete bipartite or containing a very big clique. And then you apply the two lemmas that you have seen on the previous slide. If you degenerate towards a complete bipartite graph, you use the first lemma. If either everything is in C and this is essentially a clique, or you have one very big component inside D, and this is also essentially a clique. In both these cases, you apply the second lemma, whose proof I've explained to you with this picture. And the summary I gave already indicates that I'm close to the end of my talk. And there is another use of this picture because we can just clean it up a little bit, remove the edges and add some other edges. And now you know that the talk is over.
Good. All right, so thank you very much again. I'd like to open the floor to questions and comments. So will you please unmute yourself and ask your questions.
Should I stop sharing that?
Yeah, maybe. Yeah, you could stop sharing, or you can restart if you need to refer to it. Okay, let's have some comments that match the slides.
I have a question, if I may.
Yes, please go ahead, Alan.
So in your examples of, so we saw cliques and complete bipartite graphs and things like this. So in these graphs, all maximal matchings are maximum. And so when you have shown that you have factorially many matchings, there are very few maximal non-maximum matchings. So do you know a graph that has many factorially many maximal non-maximum matchings? That's, I don't know if it's related, but so you count only the maximum, but not the maximal. So does it make a difference? Can you show also factorially many?
I think it makes a difference. It's a completely different question.
In your examples, you have
yeah, so it's a completely different question actually. So in our situation, we always look at the maximum matching, and we only achieve this by pushing parts of the Gallai-Edmonds decomposition towards either being a clique or being a complete bipartite graph. So this doesn't mean that the graph looks completely like this. There are still small portions of the graph which make up the remaining vertices. But if you want to show that there are many matchings, maximum matchings, then you can just look at certain parts of the graph. And our argument shows that these parts are sufficiently big to get the factorially many matchings. But all the matchings we eventually consider and construct, they are always maximum and not maximal. So I think I was thinking of a construction where maybe I think there are even graphs which have a unique perfect matching and still have many maximal matchings. But so I wanted
yes,
to...
but my question is, can you have both? Factorially many maximal non-maximum and factorially many maximum matching in the same graph.
So if you have,
many of them?
many maximum matchings, then you trivially have factorially many maximal matchings, because every maximum is immediately maximal.
Yes, but I said maximal, non-maximum.
Ah, maximal, non-maximum. Ah, okay. Yeah, I think this is also possible. This should also be possible. So imagine that you have, for instance,
so, just...
so actually this is possible, and the argument goes like this. So take
you can just add lots of disconnected double stars and
something like this, but you can also take a big clique, and then you add of even order, and then you add a path of length 2, and then every maximum matching must contain the last pendant edge. And it can be completed in factorially many ways in the big clique. But now if you look at the neighboring edge, then your matching will at most have one edge less than a maximum matching. You consume one vertex from your big clique, and you can still have factorially many ways of completing. A little bit less, but still many ways of completing that edge that doesn't belong to any maximum matching. So the answer to the question is yes. No? And I think if you...
So what is your example again? What was the example?
You take a clique, a big clique of even order, and now you take a P2, and you connect one vertex of the P2 by one edge towards the clique. Every maximum matching contains the pendant edge, which has a vertex of degree 1 in it, and some perfect matching of this big clique. But if you now look at the matching, the maximal matchings containing the neighboring edge, which connects the degree 2 vertex with the guy in the clique, then you can fill it up with not quite the same number of edges from the clique. But the example that Vinicius was giving, you can also do this. And if you do this, then you can push you can increase the gap between the cardinality in the maximum matching and the cardinality in the maximal matching.
Yeah, thank you.
But I think it should even be possible to have graphs with a unique maximum matching, but many maximal matchings. So I was trying to think of something where you have small components and you line them up in a linear way, and for the maximum matching, you always are forced to take the bridges. And if you don't want to have a maximum matching, you can maybe do one of two choices in each of these building blocks. So I think if you do this, then you can have a construction where there's essentially one maximum matching, which forces you to take all the edges by some parity reason. And if you go one step to the left, you have these small building blocks, and maybe you have a certain number of choices there, which you can freely combine. So
could be. I see the idea, but okay. But it was just a question. Okay, thank you.
Selina.
Thank you, Dieter. Thank you very much for the beautiful, wonderful talk. I just want to try to make a connection between the book and your beautiful chapter, and your talk today. So, as you said in the beginning of your talk, the chapter is about these restricted matchings, and today you talked about ordinary matchings. But I was wondering, since today you talked about counting these ordinary matchings, whether it makes sense to count in a way your restricted matchings according to the many restrictions that you talk about in the book. Could you please comment on that?
Yeah. So of course this question makes sense, but I think it will be much, much harder. So a key message, once you know what we have been doing, is that the key ingredient is really the Galli-Edmonds decomposition, which really allows you to split the argument in several steps, and you have a very clean idea at the very end what your proof is doing. So you push parts of your graph to be a big clique and things like this. And there is no comparable result. For instance, if you think about induced matchings or uniquely restricted matchings, you don't have anything which has the strength of this Galli-Edmonds decomposition. And that's really a key ingredient. If you think about, for instance, induced matchings, then they are closely related to independent sets in the square of the line graph. So I think that for these restricted matchings, many of the counting problems are more like counting the maximum independent sets in certain types of graphs. And these problems are also very, very hard. So we didn't study this because here the key was that we look at classical unrestricted matchings and we exploit this beautiful result by Erdős and Galli and the Galli-Edmonds decomposition. And you don't have this for the other situations. You don't even have these extremal. I think you have some of the extremal statements that you need, because in order to do a similar thing, for instance, for induced matchings, you would have first to answer the question, if you fix the number of vertices and you fix the size of the largest induced matching, how many edges can your graph have? Then you get a certain number, which depends on both these values. And then you can look at the corresponding graph and ask yourself, okay, if you have this extremal situation, do you have many induced matchings of that size or maybe just a few? And if you have many, then you can try to ask a similar question, say, now, if you're not at the extremal value, but just close to the extremal value, is your graph somehow forced towards this configuration? And still you have many induced matchings, which are largest possible. But I think, I fear that there might be some tricks that you can play that are not possible with ordinary matchings, which might destroy the symmetric results. Because if you think about induced matchings, for instance, the restriction is very strict. If you just add, so here, if we have one edge more, one edge less, we can maybe by local changes, we can take care of this. And it doesn't really affect the global number of maximum matchings. But in the induced setting, the structural restriction is so strict that already a small change can change the number completely. So it makes sense to look at the same questions, similar questions. It makes sense to count these restricted types of matchings. We didn't do so. But there are some intermediate results that you should look at in between, maybe extremal questions, fixing the number of vertices, the size of a largest restricted type of matching, what is the largest number of edges, and then you can go through these mechanisms. But I think it will not be as beautiful and smooth once you know how to do it as for classical matching.
Thank you, Dieter. Thank you.
So this is a great example of a great question and a great answer, but it's also an example of quantum physics. Why? Because I was thinking of exactly the same question, and I'm sitting here in Israel, and Selena is sitting there in Rio de Janeiro. And and both of us have this question, but by her asking it, it destroys my question. So we have a perfect example of quantum physics, or quantum computing, or
I'm
quantum
sorry, Marty.
combinatorics. No, I'm very happy. In fact, it made me so happy that that I could come up with a question that was of Selena quality. So can we have any other comments? Jaime, do you have anything to say about matchings?
Well, great talk. What can I say about it? Great talk and great answers for
Yes.
all the nice questions.
Good.
Very nice answers, actually.
So if you look at the paper, so the paper is actually in Marty's announcement, you see the archive link. I think so. What the paper does, it is a first. It shows the effect. If you're close, then you have many matchings, and the functions are already of the right type. So you have these factorial behavior, which is what you want. But of course, you have these constants that appear in there, and you have these estimations, and the argument in the paper is as short as possible to achieve this result. And I think this topic is very nice, and it's classical, and it concerns some classical objects. Maybe it would be interesting to tighten the screws in that argument and try to figure out the right answers. So not just, okay, it's factorial, but if you look at two functions that have factorial growth, you can still have quite a difference between the actual values. So I think if you look at this, this is a beautiful problem to study. And my feeling is that there should be much more precise results that will require deep insights into the structure of the graph that we didn't have. So you see already the result, the lemma that I've explained to you. So this is something that once you know how to do this, this is really very short proof and very simple argument. But it gives you the right behavior. If you like the problem, then maybe you can look at the paper and try to figure out how to improve the results and get the best possible in some sense, or closer to the right answer.
Very good. Very good. So everyone can has the opportunity to look at the paper with the link. Vinicius, do you have something you wanted to say?
Yeah, I have a couple of questions. I think they're somewhat related. So the first one is like that. Suppose you have a graph and you have these, you are in this nice region where you know there is a factorial number of maximum matchings, and you have a promise that the graph has this size of maximum matching. I was thinking about algorithmic applications. So is it possible to find a faster algorithm for finding a matching in this context, like linear time, maybe a probabilistic argument or something like this?
This is a nice question. So, the question would be, if you're guaranteed that your graph has many maximum matchings, can you find one faster than the classical algorithms?
Yeah.
And I think this is a very beautiful question, but I have no answer to this. Yeah. So of course, in some sense, if you say, okay, your graph is really like having lots of maximum matchings, one approach would be, okay, try to grab one greedily, but or do some random thing, and then with very high probability you end up with a good one. But that's just I wouldn't have any idea how to make this precise. So this is actually a very nice question. If your graph is guaranteed to have lots of maximum matchings, can you avoid going through the polynomial yet complicated algorithms and find it faster? I don't know. So it's a very good question, but I think but it might be very challenging to do something.
Because you would also have to have some kind of guarantee that the thing that you picked was really maximum.
Yes. So maybe if somebody tells you the matching number.
Yeah, I was assuming that you were given the matching number as well.
Right, but you're not necessarily in his in Dieter's framework. You're not necessarily given the matching number, right?
But I don't. So even if you know the matching number and somebody guarantees to you that you have lots of maximum matchings, I don't know how to quickly find one. And
another question is like this. So suppose you are in the, assuming that the maximum matching has a given size, looking just at the number of edges, you know that you should have lots, factorial number of maximum matchings. But suppose you don't know that, but you just know that the maximum match is at least this amount. So now I don't have the guarantee that the maximum match is exactly mu n, but at least mu n. But the edge number, it's in the right range. So could you say something about this kind of graph? For example, there are not factorial many maximum matches, but at least factorial many matchings of the right size.
So with the arguments that we have, we cannot say anything about these graphs. So for instance, if you say somebody guarantees to you that the matching number is at least 0.1n, but in fact the matching number is almost perfect matching, then the arguments we have, they don't force lots of structure, because they only force lots of structure if everything is essentially very close to that extremal configuration. So for instance, if you look at the Galli-Edmonds decomposition, and you actually have to use the real value of the matching number and not that guarantee, which might be much smaller, then I don't think you can exploit the arguments that I use to help in that situation.
So K could get much smaller. And...
Yes, yeah.
I see. Thank you.
Right.
Marty, I have a.
Go ahead.
It's slightly connected to what Vincius asked, but also different. We have the famous Dirac theorem, which guarantees a perfect matching once the minimum degree of the graph is more than half n. Sorry for the noise here. I'll just mute now. Does that also guarantee many matchings, or it still guarantees only one matching?
I think this should guarantee many matchings. So it guarantees a Hamiltonian cycle, at least 2 matches. but I think I'm pretty sure it does. Now that you say this, this reminds me of these other results that come from pancyclicity questions. So you have this result that if the minimum degree is at least n½ then either your graph is pancyclic or it's a complete bipartite graph and it is slightly off. In that situation, you immediately get many matchings. But all these arguments, they come from the. So I know this from the area of Hamiltonian cycles and pancyclicity, and there you're only concerned with, do we have at least one object of a certain type, and not do we have many. But I think if you satisfy this Dirac condition, so the minimum degree is at least half n, then you should have many maximum or perfect matchings in that situation.
Any further question, Deepak? You're fine? You're fine? Okay. Very good. Then if we have no more comments or questions, then I'd like to thank everybody for being on the call today. And let's give another big round of applause to Dieter. And I hope that you'll look into the questions further that were discussed just now and get together on your own in smaller groups as the week or weeks pass. And I wish you everyone a good week. And see you next week for Selena's talk.
It's also related to the book, to a book chapter, no?
Yes, yeah.
Well, you'll see. You'll see. It's not so related, right? It's not so related. I apologize for that, but actually it's related to something that Vinicius pointed to us. Remember, Vinicius, is thanks to you.
Very good. Okay, so we'll see you next week.
Bye-bye.